So dear, welcome back. This is our machine learning lecture number 11. Today we are going to discuss about a simple but useful concept of running gradient descent algorithm in a healthy manner, that is called feature scaling. Okay. In the last class we have discussed that how to monitor the health of the gradient descent algorithm. Time to time you can evaluate the J with epoch, that is what is going on to our cost function. Okay. The value of the cost function, of course, should be decreased, okay, epoch after epoch, and what is happening to W parameter, okay, because W parameter you are updating, okay, like this, as you know, that Wj assigned to earlier Wj minus alpha j Wj. Now this W value should be actually either monotonically increasing or monotonically decreasing. The concept is very simple. Say this is my Jw and this is W, okay, and here is my optimum W, okay. So if somebody selects initial W in this zone, then of course iteration after iteration the value will increase. If somebody has started from this zone, iteration after iteration value should decrease. And remember, this is true for only for batch gradient descent algorithm. In case of stochastic gradient descent algorithm, there will be some variations of W, as you know from the contour plot. So you can give a bandwidth that, okay, if W is varying within this range, so it's still fine and my algorithm is running quite okay. Okay. One more thing you will have to take care, which is called feature scaling, which is very common for a given data, training data set. Say here housing price data set, a typical example, floor area, the features, bedroom features, bathroom are the features, and number of story. These are the features with which the value of the price of the house depends. Okay, and you see some entries in some features column like floor area, they are quite big, in the range of 1000, and number of home, number of bathroom, number of story, they are quite small in comparison to this. Now if I try to run, and for each feature, you know, you need to assign a parameter and need to run the gradient descent algorithm, and if I am doing with the raw data, then there is every possibility that convergence will take a lot of time, and that's not a good idea. So that's why a pre-processing you need to do, which is called feature scaling. The idea is very simple. Replace, say in floor area, replace every data with the data minus mu, or the average of the data under this column, and divide by the range. This is known as mean normalization. So you calculate the mean value and deduct this mean value from each feature value. Okay, and this is incidentally is very important idea, which in machine learning you will use it again and again. This is called data pre-processing. This is called making zero mean. So you are subtracting mean from each sample, okay, so as to make the mean 0. Okay, so this is a good pre-processing technique, and divide it by range. Okay, take the example, say 5850 will now be 5850 minus the mean of all these values, 5850, 4000, 3060, 6000, 6050, 6360, all kind of thing. You calculate the mean and divide it by the range. Maximum is 6650, minus minimum is 3060. So this is This is analogous to actually x minus mu divided by standard deviation. We are dividing it. Okay, so this will actually normalize all the values of a particular column, and you can go ahead and do it for all other columns, but some columns may not even need it. You decide that in the feature scaling, your feature values, you will allowable feature values will be ranging from plus minus 1 or plus minus 2 or plus minus 3. So in that context, you decide that which feature scaling is required from the training data. So by studying the training data, this will be actually determined. So with this feature scaling, if you run gradient descent algorithm, then the convergence will be faster. We will check how it will behave. So these are some very simple sketch we have drawn. So this is this plot means the gradient descent algorithm is running in a healthy manner, because with number of epochs, number of iterations, the functional cost function value is decreasing. Okay. Again, remember, this is a typical example of batch gradient descent algorithm. In case of stochastic gradient descent algorithm, there will be some variance, and you will have to take care of giving some bandwidth. Okay, within this variation, I may accept it. Okay, this is true also for the parameter W. Okay, I told earlier that parameter W should either monotonically increase or decrease. That may not be the case for stochastic gradient descent algorithm. There will be some flickering. Okay, and you can, by the very nature of the algorithm, the way it is running, okay, taking a step for every sample, okay, and you supple the data, so that makes some kind of jittering of the flickering of the values. Okay, and of course this one is an unhealthy way of running the gradient descent algorithm. The probable cause might be that you have taken large alpha values, and that's why it is actually unstable. Learning itself is unstable. So to control it, you should check that alpha with smaller alpha values. Okay, and this is a typical plot again without feature scaling. If somebody is trying to run the gradient descent algorithm, then this is the contour plot, which is elliptical in nature. You see the physical significance of it. Actually, if somebody is starting from this kind of initial values, then they may converge faster. If the initial values are selected in this range, then the convergence will be slower. And nobody knows that why it should be. Nobody knows that where I actually should select W1 and W2. Whimsically you select them, right? So this kind of nature of the contour plot is not desirable, and this will happen when you do not do feature scaling. But if you do proper feature scaling, then the contour plot will be almost circular, circular in nature, and then wherever you select W1, W2, it should converge in a quicker manner to the minimum value. Okay. Another issue is associated with gradient descent algorithm is actually improper assigning the values. Okay, and sometimes debugging such code is very difficult if this mistake is happening. You see, this is my gradient descent algorithm, the way it runs. Okay, and the upgradation of the parameter is taking place like this. For example, temp1 is assigned value for W1 minus this is the increment which is happening, that is derivative of cost function, and then there could be n number of such parameters, right? If there are n number of features, could be n number of parameters. So first you should all compute the temp values, and once it is done, then only you should go ahead and increment or assign those temp value to the respective parameters. Okay, and this should be followed epoch after epoch. But unfortunately, if by mistake somebody is deciding that okay, this is feature 1, I have calculated, my algorithm has calculated, incremented the value of W1 Okay, and next immediately with that value I upgrade W1, okay, and then I will go for another feature W2 and then compute like this and then upgrade it. So this is very long way of running gradient descent algorithm. The logical reason could be visualized from your contour plot. You see the way the algorithm is actually converging each epoch W1, W2 as a tuple it is moving W1, W2. So the increment or decrement to these values should be simultaneous per epoch. But if you follow this the wrong way, that means you calculate in a particular epoch W1 and assign this W1 to temp1 and then immediately you assign the temp1 value to W1, right? Then when you are calculating the next parameter, the j value, the value of the cost function already has increased with incremented W1, okay. So I think you understand that, right? So you already upgraded it and then j value has been upgraded and then you are derivating that. So it will be a mistake, and that algorithm, the result you will get something, but that is not definitely gradient descent algorithm, okay. So having said that about gradient descent, that's wonderful algorithm, and you will you have been given assignments, okay, already to practice those algorithms and experiment with those algorithms. Now we are introducing you with another very interesting algorithm. This is called locally weighted regression algorithm. This could be the nature of some samples, okay. Again in COVID-19 context, suppose this is the dynamics of the spread of the disease across different countries in the world. So this could be a country A, okay, up to this, and then this could be already in a country which already suffered that, okay, they are decreasing number of infection, some other country is now picking up. So this is the dynamics of the sample, is the dynamics of some data, okay. Now in this complicated scenario, how can I design, still using a linear regression design and hypothesis, so that I can predict correctly? The idea is design locally linear regression hypothesis, okay. Say for example, I have been asked to predict the value of this x, okay. So what I will do, in the vicinity of this x, I will take some sample, I will feed my through regression, I will fit my predictor, okay, and this predictor I will use within this local range of x. On the contrary, if somebody is asking me to predict the values in this zone, okay, so what we are going to do, we are again in the vicinity of this sample, we are going to run or design another hypothesis or predictor, okay, maybe this predictor is this, and within this local range this predictor should be used for predicting. So this is actually, if this is tiny, then this could be actually model that with a linear fit, okay. So this is also, even it is nonlinear, linearization of this nonlinear problem, okay. And I will take a just digression from here to give you a similar example in physics. What we do, say simple, this is a simple pendulum, and this is direction of motion, and this is the direction of inertial torque for this displacement in this direction from the main position of equilibrium of this pendulum bob. Then using D'Alembert principle, I can deduce this is the dynamic equation, okay. And then my equation becomes I equal to ml square, so equation becomes theta double dot plus g by L sin theta equal to 0. And this, solving this equation to get a plot theta versus t, that means when the at what time where will be the pendulum bob, is extremely difficult, because this is nonlinear second order system, okay. and sin theta is a series, so I cannot solve this easily, right? So what we do, we normalize. That means we replace sin theta with theta, assuming that theta is very small, normally 4 degree, and then my life is easier. So this, I have an equation this, and then I can solve it, and this is a circular frequency. Okay, from there I can calculate the time period, which is very well known to you, t equal to 2 pi root over L by g. But remember, this is only valid locally when your pendulum bob is undergoing a small displacement. If it is undergoing a large displacement, this same formula will not be valid. That perhaps in your school you have checked it during experiment, right? So this is actually linearizing a nonlinear system helps, right? It makes the problem simpler. Here also, you see, nonlinear dynamics of the sample we linearized. We always are fitting in the locally weighted regression. We are fitting always a linear predictor, okay, and that still can work. So this is a basic idea, and it is very useful in many cases. Okay, now how the algorithm is designed. Okay, you see, this is my cost function j. Okay, jw equals to summation of sample I equals to 1 to m hw xi minus this is level yi. So this is samples, okay, square. So this is my normal j. What we do here you see, with a function called gamma, okay, with samples we multiply, okay, this function with gamma, and we defined that function, weighted function gamma, okay, that is locally weighted, okay, weighted function gamma, like e to the power minus xi minus small I, that is we will discuss, equivalent to the samples here, square divided by 2 tau square. Tau is the bandwidth. So this is actually a function similar to Gaussian probability density function, but only structural similarity. This is not probability density function. So what are the elements here? You see, xi, these are the samples, okay, and this x actually is where I need to predict, okay. So this x, okay, so in the vicinity of this x I need to design this weight and divide by 2 tau square to make similarity with Gaussian distribution. The formula is like this. It's called bandwidth, which controls how fast the weight will fall with the distance, okay. So you please remember this, okay. So there is a weight assigned multiplied with my earlier linear regression function, cost function, okay. Now what is the role it is playing? Okay, say if this is very small, then what will happen? E to the power very small closing to 0 values actually is telling you that gamma value will be 1. That means you use the same function as our linear regression function, and if this is very large, then gamma will be 0. So gamma varies between 0 and 1, and how it varies? This is the nature of the gamma function. You see, is again Gauss separate, Bell separate function. What it is telling? Now say these are my samples. These are my samples, right? These are samples, and these were actually y, this is x. Now suppose I have been asked to design a algorithm, a predictor in the vicinity of this x. Okay. So what I am trying to do now, I will have to, and these are my samples. I am trying to do with this gamma function. What I am trying to do, I am trying to give weightage of my neighborhood samples. Okay. So what we are doing, this will be weighted now by this value. This is very close to my for my sample x, for which I need to design. So I will get maximum. So this much weight I will give to this value, like this. So further from the value x for which I am designing the predictor, further away from that value will be getting low weight. Further nearer will get more weight by virtue of this Bell-shaped function. Okay, the way we have defined it. Okay. And then is linearization. Okay. Then if we select very small bandwidth, tau is very small. Okay. Say what that does it mean? Means now you will have a Bell-shaped like this, very small. Okay. And if this is large, then Bell shape will be like this. So that the meaning is, this is x for which you are trying to design this algorithm, that is a predictor using algorithm, locally weighted algorithm. So what it will do, if it is trying to accommodate more number of samples, then you need to play around with this tau value, make it large, so that Bell-shaped curve will be flattened. And if on the contrary you want that no, I will design the predictor only in the vicinity of, small vicinity of the x, then you will design tau with small value and it will be stiffer Bell-shaped curve. So that will mean that, okay, very small number of samples around x you are allowing, and the tau large means wide range of samples you are allowing. And of course this has this has some influence in overfitting and underfitting problem, which we will discuss next. So tau small will actually cause overfitting problem, because these values the predictor will be plagued with very small number of samples which are in and around x. Now if tau is on the contrary large, then it will be plagued with underfitting problem, because large number of values around x you are accommodating, and still you are considering a linear predictor. Okay. So playing around with tau values, you can make a best fit predictor. Okay. So this is all about this algorithm. It is useful for dynamic samples. Okay. In robotics, it has application. For example, robot locomotion, the hip joint is varying sinusoidally, and sometimes the knee joint has double hump like this. Okay. It is double hump like this. Okay. So this kind of time series data we can predict using locally weighted regression. Okay. So you can actually you will have to practice the implementation of locally weighted regression, linear regression. So here only thing is the weight, a peculiar sept, very well designed sept weight, which is multiplied in modifying the JW. Okay. And once it is done, once properly you select tau values, okay, and then decide and you are given that this is designed in and around x, then of course you run gradient descent algorithm, because after that, once the J function is constructed, okay, then same old story. Okay, you differentiate this and run the gradient descent algorithm. And incidentally, this algorithm is known as non-parametric algorithm. Non-parametric algorithm. Okay, why this term? You know, it is a non-parametric predictor. Non-parametric type of. Earlier, which we have learned in linear programming, they were parametric type. Okay, so I'll just touch upon this. So this was actually our plus W2 X2 like that. Okay, and we are using samples to design the hypothesis, and once the design is over, these parameters W0, W1, W2 are fixed. They are not changing with the sample. Okay, but here in non-parametric form, W0, W1, W2 still are there, but those are changing with the sample. For example, here you have a hypothesis 1, say for example, and some parameter which is regionally valid. Then you have another region parameter, and they are valid for another region. So all these parameters number are increasing with the variations of with the samples. Okay, so more the samples you consider, more number of parameters will be there. So parameters are dynamically varying. That's why it is called non-parametric form of algorithm. Okay, and one advantage of this is actually it can capture the dynamism of the samples, as I said earlier, and by just taking into consideration of suitable bandwidth tau value, you can design a best fit hypothesis. So these are the advantage. Disadvantage, of course, in machine learning, as you know, that everything has there's no free lunch. The disadvantage is the entire sample together with large number of predictor has to be on the computer memory. Okay, if you try to predict in a particular zone. For example, a particular country, I want what will be the dynamics of COVID patient in next couple of weeks. So if I have all the country's data with me and the corresponding predictor designed for that particular country, then only if somebody asks me, okay, go ahead and give me the data for country number A. Okay, so I will have to just see what is the predictor corresponding to country number A, and I will have to retrieve, okay, I will have to predict using that predictor. Okay, so this is computationally not very friendly. Okay, so that's the only disadvantage or cons you have. Otherwise, this is a very elegant algorithm which you will implement, and I believe the simple concept of this you have learned in the linear regression. Well, so a lot of things you have learned now in a simple way, and in the next class we will talk about the regularization, very important concept. Okay, so you see, using linear regression model, all the terminologies and all the procedures of machine learning tools and techniques, all the detail about the process you are learning. Okay, and if you have any problem, come to the discussion forum, and my TAs and we will be ready to help you. Okay, so till then, stay safe and goodbye. Have a nice day.